Yeah, I'm here. I'm just going
Uh,
to share my screen.
okay. Parvesh sir, are you listening? Parvesh sir?
Yeah, I'm
Yes, sir,
here.
you are audible, sir.
Okay, okay. So, session is recording already done, na? Or
Yes, yes,
we are
continue the.
recording
Yes,
another
yes, I am also
lecture?
recording.
Okay, thank you. Okay, ma'am, you can start now. Thank you.
So, good evening, everyone. My lecture is about the soil improvement using stone columns, it's the techniques and the benefits. So, the first thing is, what is problematic soil? Some natural soils, they do not have enough strength, stiffness, or stability to support buildings or structures safely. And these types of soil often settle too much. They don't drain water properly, have low resistance to force, or they can be easily compressed. So, because of these problems, we cannot build directly on them unless we first improve the ground. And these soils are called as the problematic soils. Let us talk about some of the problematic soils. If you will see the soft clay, what are the problems here with it? It is very weak, it holds water, it settles slowly and can't support buildings well. That's why. Silt becomes weak and slippery when wet, and it doesn't drain water properly. Expensive clay like black cotton soil swells when wet and shrinks when dry. So these movements can crack the buildings. Collapsible soils look strong when dry, but again, they suddenly sink when they get wet. Marine clay is very soft and takes a long time to settle with poor drainage. Dispersive soils break apart easily in water due to salts, causing erosion and washout. So these types of soils all need improvement before any construction can happen safely. So for different types of the problems, we are having different ground improvement techniques. Okay, so if you will see, uh, here I am going to concentrate on the stone columns. So focusing on the stone columns, these are generally used for soft clay, stiff clay, silt, and silty sand. They help in improving the bearing capacity, reduce the settlement, and also they allow the drainage. So, but if our soil is very soft or just like a peat or soft clay, then stone columns may not be enough. Then we need to strengthen the stone columns also. In that case, we can go for the encased stone columns, and generally geotextiles, they can be used for encasing the stone columns. So again, geosynthetics, when they are used for encasing, they make even the weaker soils uh, uh, pro, able to get stabilized through the stone columns by improving the confinement and the load transfer. What are the stone columns? So some brief introduction was given by Professor Cole also in the previous lecture about. So these are widely used for ground improvement techniques. So stone columns are the vertical columns made of compacted stone particles installed in weak or loose soil to improve its performance. So they strengthen the ground and they do not act as foundation itself. So this is the difference between, if you say what is the difference between the piles and the stone columns. So stone columns are not the foundation itself. So these are not shallow foundations, these are not deep foundation. It's purely a soil improvement technique. Okay, so here the process involves replacement of the weak native soil with the densified column of aggregate, which provides more strength and stiffness. And the improvement in soil strength comes mainly from the stiffness of the stone column, which helps in distributing the loads and reducing the settlement. So here on the right hand side, you can see the illustration showing the construction process and a real life site where stone columns are being installed. What are the merits or advantages of stone columns? First thing is they offer rapid installation. These are very cost effective. That's why these are popular choice in many construction projects. Secondly, they improve the load bearing capacity of weak soils and effectively reduce settlement, which is crucial for supporting the structure safety. Again, they are versatile. They are suitable for stabilizing various types of the soils like soft clay, silts, loose sands. They cause minimal disturbance to the ground and they are considered environmentally friendly compared to more invasive methods. And further, by encasing the stone columns, we can further enhance their strength, their confinement, and their overall performance. So, again, you can see the various, on the right hand side, you can see the various soil improvement techniques. But again, we can say that these stone columns, they stand out for their simplicity, efficiency, and adaptability. So, types of the stone columns. So, depending upon how they uh, are resting. So end-bearing stone columns, if you will see, they extend through weak soil into the firm stratum or bedrock and transfer the loads directly to the stable layer. And generally, these are constructed by driving columns until reaching firm strata, ensuring stability for heavy structures. But floating stone columns, they are generally embedded within the weak soil without reaching the firm layers, relying on surrounding soil shear strength. And again, commonly used for lightweight structures, roadways, and embankments where deep foundations are uneconomically. So you can see both types. One is reaching up to the hard strata and other is just floating in the soil. And there are different installation methods of the stone columns. Displacement method, a non-displacement method, and a vibro replacement method. So generally how the soil moves when we are going to install the stone columns. If it is just in displaced, then it is the displacement method. If we are not displacing it, we are taking it out, then it is a non-displacement method, and then the vibro replacement method is there. With the help of the vibro float probe, we create the hole which densifies the adjoining surface and soil, and then stone filling is done with the help of the vibrations. So now I will focus on the basic design parameters of a stone column. So installation of stone columns in soft cohesive soil is actually the self-compensating process. Self-compensating process means softer the soil, bigger is the diameter of the stone column. Now, due to the lateral displacement of the stones during vibrations or ramming, the completed diameter of hole is always greater than the initial diameter of the probe. Because softer soil, there more displacement can be there, so diameter is always more. And how much more, that again depends upon the undrained shear strength, stone size, characteristic of the vibratic probe or rammer used, and the construction method. Second thing comes the pattern, how these stone columns, they should be arranged. Now, stone columns should be installed preferably in an equilateral triangle pattern. The first figure you can see here, the spacing S you can see, and this pattern is known as a equilateral triangular pattern, which gives the most dense packing. Otherwise, we can use the square pattern also. So typical layout is an equilateral triangle pattern. So here you can see both the types of the patterns, and you can note down how the spacing S is there in both the patterns. Then spacing, if we talk of the spacing, the design of the stone columns should be site specific and no precise guidelines can be given on the maximum and minimum column spacing. But broadly, you can say that the column spacing may be from 2 to 3 depending upon the site conditions, loading patterns, column factors, and installation techniques, etc. These all things need to be taken into account while deciding the spacing. When we will design any single column, we will use one term, which is equivalent diameter. So the equivalent diameter, if you will see, again, here you can see what is equivalent. So the tributary area of the soil surrounding each stone column forms regular hexagon around the column. It can be seen in the first figure when the triangular arrangement is there. So this hexagon, it can be closely approximated. Yes. So it can be approximated by an equivalent circular area having the same total area. So then the diameter of that circle is known as the effective diameter, DE, and it is generally 1.05 times the spacing for equilateral triangle pattern and 1.13 times the spacing for a square pattern. Next term that is used is the replacement ratio. And again, to quantify the amount of soil replaced by the stones, we use the term replacement ratio. So generally it is, you can say AS upon A, means area of the stone column upon the total area within the unit cell. Now this total area of the unit cell is what? Area of the stone column plus the area of the ground which is surrounding the column. So that ratio is the replacement ratio. So we can go to the next term, which is the stress concentration factor. So it is given by small n. Again, stress concentration occurs on the stone column because it is considerably stiffer than the surrounding soil. So from the equilibrium considerations, we can find out the stiffer stone columns should be giving us the greater stress in the surrounding soil and so on. So when we say that if we are having the externally applied load sigma, okay, then we can also consider the in the soil, if we consider the stress, that is sigma g. Then in stress taken by the stone column to the stress taken by the surrounding ground, that ratio is n. And generally this value lies between 2.5 and 5 at the ground surface. Failure mechanism. Single stone column, if you will consider, then if it is loaded over its area, then how it fails, that failure mechanism will depend upon the length of the columns. For columns having length greater than its critical length, and what is that critical length? That is about 4 times the column diameter. Okay, then whether it is an end bearing or it is a floating, it will always fail by bulging. Okay, long column, or you can just say that long column, whether it's end bearing or floating, it will always fail by bulging. But the column which is shorter than the critical length, that generally fails in general shear. Again, if it is end bearing, then general shear will be there. But if it is a floating column, then it will fail by end bearing. Okay. So when we have to design the stone columns, and we have to keep in mind some general points. So the first thing is how we calculate the lateral confining stress. So here we always assume a triaxial state of stress. That stone column is there, and then the surrounding soil is also there. So at the failure, the triaxial state of stress due to the stone column and the surrounding soil, it is considered. And if sigma 1 is the ultimate vertical stress which stone column can take, then we can use this equation where you can say that phi s, that is the angle of internal friction of the stone column. Okay, and sigma 1 by sigma 3 is the coefficient of passive earth pressure, TP of the stone column. Again, here we are assuming a plane strain loading condition. Second thing is, what is the ultimate load capacity and the settlement? Uh, we have to approximately estimate the ultimate load carrying capacity on the basis of the soil investigation data or by the test loading. Okay, so preferably we determine the initial load test on the test column installed, especially for the purpose of calculating the ultimate load. So we will install one stone column for testing prior to installing the all columns. Then comes the environmental factor. Again, environmental factor like if some aggressive environment is there or some agent like that is there, what is the condition of the groundwater there, what are the chemicals in the subsoil, all those factors, they are taken into account. Next point is load test result. Again, the settlement of the stone column at safe working load from load test results on a single column, we should never forecast it, okay, from the settlement of the structure. Yeah, sometimes it may be there that familiar foundations or familiar structure is there in that area, then you can take the fair estimate. But otherwise, the average settlement may be assessed on the basis of the subsoil data and loading details of the structure. Factor of safety, we have to consider some points for considering the factor of safety. For example, how reliable is the value of ultimate load carrying capacity of the column? You know, what is the type of the superstructure and what is the type of loading? What is the allowable total differential settlement of the structure? What is the manner of load transfer from stone columns to the soil? So we have to keep all these points in mind while deciding what will be the factor of safety. And generally, the minimum factor of safety for such a load test is 2.5 as per IS 15284 Part 1, 2003. So this code is actually used for the designing of the stone columns, or you can say how to use the stone column for improving the soil or stabilizing the soil. Again, we have to always apply some field controls. So when we have to, especially when we are going to use the vibro floats, we have to keep in mind the penetration depth, including the depth of embankment in the first strata, monitoring of volume of backfill added to obtain an indication of the densities achieved, and monitoring of the emitter or hydraulic pressure gauge readings to verify the maximum possible density that has been achieved in case of the bifurcated columns. So minimum field controls by measuring or monitoring these parameters is always must. Field loading tests. Now, as I told earlier, irrespective of the method used to construct the stone columns, the initial load test should be performed at a trial test site to evaluate the load settlement behavior of the soil stone column system. So for initial load test, in order to simulate the field conditions of the compaction of the soil, minimum 7 columns for a single column test and 12 columns for 3 column group test may be constructed for triangular pattern. So here you can see for the single column test, we place these columns in this arrangement. Okay, so the spacing you can see as per the code, and what is the diameter of the stone columns as per the code for field loading test. Again, here in this figure, you can see that if we have to test the 3 columns in a group for the group test, then minimum 3 columns should be tested and minimum 12 columns, they should be arranged like this. Then we perform the test to carry out how to check their load and settlement behavior. So here again, the initial and final soil conditions at the trial site should be investigating by drilling at least one borehole and one static cone test, or the pressure meter test or the dynamic cone test should be done to assess the properties of the soil. After that, a granular blanket of medium to coarse sand having thickness not less than 300 mm should be laid over the test columns. Okay, first of all, the test columns, they are prepared, and over that we have to put a blanket of the coarse sand. The thickness should not be less than 300 mm. Okay, and over that blanket, then we have to provide the properly designed footing. Okay, so again, we have to keep in mind everything. What would be the high water table conditions that will exist at the site, everything. And then we will start the procedure of applying the load. So if you will see the elevation, then it will be like this. Okay, so that was the plan. Now here you can see the elevation for the test condition. Now the load has to be applied to the footing by suitable can sledge. Okay, so no impact should be there, no fluctuation should be there, and no eccentricity should be there. And minimum 1.3 times the maximum test load, we have to provide the load over the Kent ledge. And then again, load settlement observations, will be taken up to the 1.5 times the design load, and settlement will be recorded by 4 dial gauges. Okay, and sensitivity of each dial gauge, it should not be less than 0.02 mm. And we have to keep these dial gauges diametrically opposite ends of the footing. So 2, these are visible to us, and 2 are perpendicular to this. Okay, so 4 dial gauge we will be taking, and we will take their average. Again, we have to apply the load in 5 stages. So in each stage, we will apply 1/5 of the design load, and it should be maintained till the rate of settlement is less than 0.05 milliliter per hour. And after that instant, next stage of the loading should be applied. Again, the design as well as the maximum test load, that has to be maintained for the period of 12 hours after stabilization of settlement to the rate. Load settlement and time settlement relationships, they can be plotted from the settlements observed for each increment of the load. For example, we can take the reading at 1 minute, 2 minute, 4 minute, 8 minute, 16 minutes, half hour, 1 hour, 1.5 hour, 2 hour, 3 hour, 4, and like that. Okay, and these intervals that may be modified if you desire. And after taking at each time and each load, you can note down the settlement, and then we can plot the graphs. So after doing the or increasing it in at least 5 stages, then we have to load test. It is continued for 10 to 12 mm settlement at design load for the single column test, and 25 to 30 mm settlement at the design load. Okay, for a 3-column group test. Now, for example, we have to do the routine load test. There are few job columns. They may be tested only up to the 1.1 times the design load intensity and minimum cantage of 1.3 times the design load. So one of my PhD candidate, Parvez, he's doing work on the stone columns. So he has developed a small model for testing the stone columns. So here, that is a test arrangement. A tank has been constructed in our lab. And here he has filled it with the kalonite clay, and then you can see the arrangement. The hydraulic jack has been used to apply the load, and the settlement is taken with the help of the dial gauges. So this is the total arrangement where he's uh, plotting the load settlement curve for the test tank. So this test arrangement has been made in our geotech engineering lab. So he's working on this. Okay. So after we can plot the settlement and pressure, then we can record the all the data. Now, here is the work done by a few researchers. If you can see, they have plotted the pressure and settlement curve for different types of the columns. So here you can see the stress strain curve, settlement pressure curve for unimproved soil also. For, you can see the ordinary stone column, OSC, if you will see, and ESC is the encased stone column for different types, for the same surrounding soil, for the same material of the stone columns. Okay, so but how the encasing of the columns that affects, so that effect is clear in this graph. So firstly, what is happening there? That encasement is providing additional lateral confinement to the stone column, and this improves its strength. It helps, it resists deformation, especially under the high loads, when high load is there, or the soil is very weak in both the cases. Okay. Secondly, the encasing material, it helps to prevent the loss of the stone particles. Otherwise, when the loading is there and the surrounding soil is very, very weak, then what will happen under the load? That stones, they will be displaced into that soft soil. So it will lose its shape, and when it gets damaged, it is not vertical, then it is not going to transfer the load, or it is not going to give the proper stiffness, because how much improvement is there, that will depend upon the relative stiffness. So that's why, secondly, we can say that encasing material helps to prevent the loss of the stone particles into the surroundings of soil. And but it is important when the soil is loose or saturated soil, where there is more loss, okay, due to the quick reduction in the strength. And third thing is, encased stone columns, they improve the drainage characteristics of the system. The geosynthetic, they allow water to seep out, reducing the pore water pressure and improving the soil's overall behavior during loading. And next, you can say that encasement, it significantly reduces the settlement, and at the same time, it increases the bearing capacity of the treated ground. So here you can clearly see in this graph on the left, ESC line, triangle markers, that shows much less settlement compared to both the ordinary stone columns and the unimproved soil. Again, in the graph on the right hand side, you can see the vertical stress versus settlement. the encased floating stone columns against secular markers, and they perform much better than both the non-encased columns and natural soil, offering higher stress resistance at lower settlements. So, these benefits, they all contribute to important outcome. Which is that important outcome? Increased embankment stability. So with stronger support and better load distribution, the risk of failure due to foundation instability is greatly reduced. Again, so it highlights the importance of the encasement, that it does not only improve the strength and drainage, but it also ensures long-term performance and reliability of the ground improvement system. Then if we are saying that the encasing the columns, that is going to improve the stiffness. But then what is the effect of the encasing material? So that has been also studied by various researchers. So here, this slide you can see, it highlights how the stiffness of the encasing material that affects the performance of the encased stone columns. First, look at the graph on the left. So this shows the relationship between applied stress and footing settlement. The unreinforced soil, it shows the least performance with low stress resistance and high settlement. And as we move from ESC1 to ESC3, we see that increasing the stiffness of the encasement significantly improves the load bearing capacity. So here ESC3, it is with the stiffest material, it can resist much higher stress with much less settlement. So this clearly shows that higher encasement stiffness leads to better load transfer and improved stability. Now turning to the graph on the right. So this plot shows settlement versus applied pressure for different encasement stiffness levels in floating stone columns. So the pink curve, it is for ordinary stone columns, and they settle more under pressure. And as the stiffness of the encasement increases from 1,000 to 10,000 kilonewton per meter, curves shift to the right, indicating lower settlement under the same pressure. So this means that as we increase the stiffness of the geosynthetic material, the column becomes more effective at resisting pressure and minimizing the settlements. So key takeaway from both the graphs is simple. Stiffer the encasement, the better the performance in terms of both bearing capacity and settlement control. So again, you can see the type of the stiffness of encasing material, how it informs. Here you can see with the woven types of the geotextiles, which perform the best, showing the least settlement under increasing pressure. But ESC with non-woven geotextile, the triangles, they perform slightly less effectively, but still much better than unreinforced clay and ordinary stone columns. And the clay layer without any column, it shows the highest settlement, indicating poor performance. So here, the second trial of AC with non-woven geotextile, it confirms the consistency in its field. So this confirms that woven materials which are stiffer provide better lateral confinement, reduce and increasing resistance. So moving to the graph on the right, here you can see the bearing capacity ratio and the axial stiffness of the encasing material that has been plotted. So as the EA increases, the BCR improves steadily, going from 2.63 to 3.68. This means that stiffer encasing materials, they allow the stone column to support a higher load with less settlement. So again, the key takeaway is stiffer encasement, better confinement, it gives higher bearing capacity and lower settlement. So choosing the right encasing material, it can significantly improve the overall ground performance. Now, the different researchers, they have worked over the different lengths of the encasing. They have not encased the full length in every case. So from here, starting from with the graph on the left, you will see how load versus settlement varies for different configurations. Okay. If a plain clay bed has been used, okay, then the highest settlement under load is there, it is performing the worst. But when we add stone columns, either with stone aggregate, slag, or the combination, we see performance improve, but settlement still remains significant. However, as we introduce geosynthetic encasement and start increasing the encasement length, the performance drastically improves. Okay, if the encasement length is increased from D to 4D, the settlement progressively reduces under the same load, clearly showing that longer encasement lengths offer better confinement and better load distribution. So see on the images on the right. Okay, so these physical models, they show how bulging occurs in the stone columns as the encasement length increases. The first few images, they show visible bulging in the middle of the column when encasement is limited. Okay, but as we increase the encasement to 3D and 4D, the bulging is almost eliminated, showing much better stability and integrity of the stone column. Now, stone columns, they can, earlier, they were all, only and only constructed with the help of the natural aggregates. But just as the sustainability requirements are increasing, the use of waste material is increasing. So it is here in case of stone columns also. The stone columns nowadays, they are using the waste materials also. Okay. So if you will see, we are using the different type of the waste materials, and we are having some main waste materials which are used in the stone columns, like the tires, construction waste, silica, manganese, slag, okay, plastic, overburnt bricks, glass, steel slag. So lot of material that is being used nowadays. So this material again, it is used as a, it is generally used as a aggregate. So we have to first of all transform these materials in the aggregate form, and then we have to use this material. Okay, so here you can see what is the size range for the different of the material, and the different studies have been done on these materials. So we can compare the different waste materials also, how they have been used. Again, when we have to compare the various waste, we use efficiency. And we call efficiency as the ratio of load carrying capacity with any mix like waste to the load carrying capacity of using natural aggregates only. So this graph here shows only the best results obtained by various waste. So at in the from the different studies where we got the maximum load carrying capacity, we used that percentage of that waste, that this particular waste at this percent, it gives us the maximum density, maximum load carrying capacity. Okay, so here you can see that 20% tires with 80% of natural aggregates, and replacement of fine medium and large size tire by 20%, 25% waste concrete, 100% waste concrete, and 100% silica manganese slag. These are more effective, and 20% tire with 20% natural aggregates, that gives the best result. So different waste. This is the summary of the literature view of the different wastes used as a material in a stone column. So then we come to the conclusion. So you can see that stone columns, they improve the strength, they reduce the settlement, and they are cost effective. Okay. And we have already discussed a lot of benefits. So again, if we want to improve the load bearing capacity, or if we want to use it for softer soils, then we can go for the encasement. And generally the geosynthetics come here. Okay, so they significantly enhance the performance by confining the stone columns and allowing it to carry more load. And optimal encasement length is around 50 to 60% of the column height. And last is the waste materials. They again, if you are going to use the waste materials alone, they are going to provide the lower bearing capacity than the natural aggregates. But if we are going to use them by blending them with the natural aggregates, then obviously we are going to achieve the higher capacity than the natural aggregates, or at least equivalent to the natural aggregates. Okay, so this is the one part. Then we can move to the second part. So here we said that we have to use the stone columns. Okay, whenever we have to use the stone columns, we cannot take their value arbitrarily from other project or from the previous assignments. We need to estimate the load carrying capacity of a column. So how we have to do it, we will now go to that slide. Okay. So when we have to design a stone column, especially in the cohesive soils, then the load carrying capacity of that treated ground, it is obtained by summing up these three things. What are the three contributions to that? Contribution of, first is the capacity of the stone column resulting from the resistance offered by the surrounding soil against its lateral deformation. Okay, stone column. Second is what? Capacity of stone column resulting from increase in resistance offered by surrounding soils due to surcharge over it. And third is the bearing support provided by the intervening soil between the columns. So again, the code IS 15284 part 1 2003, it is used to estimate the load carrying capacity of the column. So here you can see that the first thing is A part. Okay, A, B, C, three components are there. First, we will calculate or estimate the component 1, which is the capacity based upon the bulging of the columns. So again, here we have to consider the foundation soil is at failure when stressed horizontally due to bulging of the stone columns, and the limiting axial stress in the column is given by then sigma V is equal to sigma R K sigma P column. Okay, so again, limiting radial stress we have to consider, limiting axial stress we have to consider, undisturbed, undrained shear strength of the clay we have to consider, initial effective radial stress, and then final, okay, effective stress and effective angle of friction of the soil, that all these factors come into account for calculating the capacity based on the bulging of the column. So second is the surcharge effect that we are going to take into account. Okay, so again, if you will see initially, this surcharge load is supported entirely by the rigid column. So as the column dilates, then some of the load is shared by the intervening soil depending upon the relative rigidity of the column and the soil. And consolidation of soil under this load results in an increase in its strength, which provides additional radial resistance against bulging. So again, it if you consider the surcharge load, what is it? The load of the sand blanket or the sand pad. And if the thickness of these elements is not known, then the limiting thickness of the surcharge loading, we have to represent it with the safe bearing capacity of the soil. And the increase in the capacity of the column due to surcharge, then it can be computed in terms of the radial stress. So here, that's why delta sigma RO is here, increase in mean radial stress due to surcharge. Again, it will depend upon the safe bearing pressure of the soil with the factor of safety 2.5. As per the code, we have to take the minimum value of the factors of safety as the 2.5. Okay, so again, this value, it will depend upon CU and NC. So when we have to calculate Q2, then we have to take factor of safety of 2 and then increase in the load of the column. Q2 is what? The increase in the safe load of the column, that is given by this expression. So here the surcharge effect is again minimum at the edges, and it has to be compensated by installing additional columns in the periphery region of the facility. So that's why when I showed you the arrangement for the test, then I showed you that for single column, we have to apply at least 3 columns on the periphery, and for 3 test arrangement, we have to use at least 12 columns. Then only we can test the group of 3 piles. So we need additional columns on the sides to find out the bearing support. And then third thing is bearing support provided by the intervening soil. So again, this component, it consists of the intrinsic capacity of the virgin soil to support a vertical load, which is generally computed by the effective area of the stone column, including the intervening soil for triangular pattern, that is taken as 0.866 S square, and area of intervening soil for each column AG, it is given by 0.866 S square minus pi D square by 4, and safe load then taken by the intervening soil Q3, that is Q safe into AG. Overall safe load on each column and its tributary soil is total Q. Q is the sum of Q1, Q2, and Q3. When we have to make the stone columns in the mixed soil, then we have to again calculate both the C and phi, and this capacity, it is generally estimated by the Bell's formula for passive pressure, and then we will use that. And the surcharge effect and bearing support of intervening soil, again, they have to be obtained like Q2 and Q3, just like in the same soil. And in the mixed soil, the only difference will come that when we have to calculate the uh, we have to use the capacity, or we have to calculate, then we have to use the Bell's formula for the passive ratio. And when we have to use the column spacing, again, if you will see the plan area of the structure, then area per column is arrived at that can be geometrically calculated, and effective spacing that can be calculated depending upon the pattern which we are going to use for the columns. If we are using the triangular pattern, then we will use it as 0.866 s square, and if it is a square pattern, then it is 1.0 s square. So again, design calculations, they are repeated till there is convergence of the assumed and the calculated column spacing. Then one or two trials may be required, and then only we can find out the spacing. And additional stone columns, they may be required inside and outside of the periphery of the loaded area, considering the pressure distribution and presence or absence of the surcharge and permissible or expected settlement of the structure. And these additional columns may be provided either as rings or at a closer spacing for an appropriate distance inside as well as outside of the periphery of the loaded area. So again, so you can use this code and its various annexes for seeing the settlement analysis. We want to do it by reduced stress method, and installation techniques of stone columns that can be also read in detail by using the IS 15284 part 1. Which is the design and construction for ground improvement guidelines for stone columns is the part 1. So I think that's all about the stone columns, ground improvement by the stone columns. So any questions?